Alright, so for our first video in the calculus series, we're going to start with limits. It's kind of hard to explain what the utility of limits are without first explaining how to use them. And since this is my first video in calculus, I'm just going to give some general guidelines about how this series is going to be run. Basically, this is just going to be the bare essentials. You should be taking a class with this. You should be doing homework problems outside of this. This is not going to be comprehensive. If you just watch this, it's probably not enough for you to really grasp and master calculus, but this should help you go over the basics and review, or, whatever, if things aren't fresh or if this is your first time taking it. So let's just jump right into it. Let's say you were asked to find, and here you'll see the notation, the limit as x goes, oh dear God, the limit as x goes to 2 of the function x squared, which is what we have over here on the right. Well, the notation might seem weird because usually, you're used to seeing something times something or addition or whatever, but this is just, you've got words in your algebra now. But all it's saying is that, so here is where x equals 2. It's just right around here. So if you were to go along your x-axis and you go from the left towards 2 and to the right towards 2, what value would you get for your function? Well, it's pretty obvious. You're going to get 4. So the limit as x approaches 2 of x squared is just 4, because that is the value of the function at 2. So for those functions that are continuous at that point, meaning it's just a basic function, it's going through that point, your limit value at that point is the function. So the limit of x cubed at 2 is 8. The limit of 1 over x at 2 is 1/2. However, sometimes your limits are not going to be at easily defined points. Maybe you're at something more along the lines of the limit of x squared as x approaches infinity. So you see your function is going, as x approaches infinity along the x-axis, y is going to approach infinity. You can't say what the point is because it's infinite. So if you were to write it informally, you might say the limit as x approaches infinity of x squared is infinity. However, the more formal way is to say it does not exist. That's the more technical answer. Limits, the limit of a number is just a number. So let's say I said, what is the limit of x squared as x approaches infinity times, or sorry, I shouldn't say infinity, I will say 3 times 7. Well, the limit as x approaches 3 of x squared is just 9. 9 times 7 is 63. So you can do algebra with limits, although normally the easiest thing to do is to solve them first and then plug them back into your problem. So limits, there's some special properties, but as far as we're concerned, we'll see some special ones as we go maybe, but for right now, you just really need to understand what it is. And we'll use them for some more calculus later on. Limits also can be one- or two-sided. So once again, if we were to look at that function x squared, what's going on? If we look at that function x squared, I could say the limit as x approaches 2 from the left, which means you'd put a little minus, is equal to 4. But I could also say the limit as x approaches 2 from the right of x squared. And since, if you mark it off, here's 1, there's 2. If you approach it from the left, you get the same value as if you approach it from the right. They both go to 4. And that is what makes that function continuous, which, that's kind of a formal definition. I mean, a simple definition of continuity is just, can you draw the function without lifting up your pencil? So that function is continuous because there's no breakages. Now, if, say, the function looked like that, that's no longer continuous because you have a breakage right there. That's called a jump discontinuity. However, to get back to limits, now let's take the limit of, we'll call that at x equals 0, of this function, just f of x. So the limit as x approaches 0, of f of x, 0 from the left, is equal to, we'll call that, I don't know, 3. But the limit as x approaches 0 from the right of f of x is equal to 0, because it's, or no, it looks more like 1, sorry, is equal to 1. So you can see the limits are not necessarily the same. Even though you're approaching the same value, if you have a discontinuous function, you can have non-equal limits. Now, when it comes to evaluating limits, we've already seen two different ways to do it. One was to look at the graph, and that is a graphical way of solving limits. You can just see, oh, this is approaching 1 right there, and this is approaching 3 right there. So you've solved the limit at 0. Another way is analytically, and that's what we've done in those examples with x squared, where you can simply plug in the number. That's a numerical approach. That's an analytical approach. The other way to solve them is numerically, and that would, usually you'd use a computer and you could see, well, it looks like if I was to have a table of values of, say, we'll go back to our trusty function x squared. Hold on, there we go. If we go back to our function x squared, I'll put that back in black to be consistent. If we go back to x squared and you were to draw a table of values, and say you've got x and y, as x is, 1.8, 1.9, 1.95, 1.98, 1.99, you can see that y is going to gradually approach, let's see, from this side it'd be like 3.99 or whatever, and you can tell that it's going towards 4. 3.98, 3.87, I don't know, I'm just making up these numbers. I mean, if you squared them you could see, but you'll see that the y values are just gradually approaching towards 4, and from the right side, if you were to go and decrease, say from 2.1 down to 2, you would see it's also approaching 4, and that would be a numerical solution. Where this would come in handy would be a function like what we have here, like the limit as x approaches 0 of sine of x over x. Now, let's think about this analytically. If you were to plug in 0 into this function, well, what's sine of 0? Sine of 0 is 0. And 0 plugged in for x is obviously 0. Well, 0 over 0, I mean, how many times does 0 fit into 0? Infinite, 0, 1, I don't know. It's undefined. So that limit cannot be solved, at least we don't know yet how to do it analytically. Graphically, you could of course plug it into your calculator and you could look. However, assuming that's not allowed on a test, maybe you could plug in sine of 0.0001 divided by 0.0001, and what you would get is some answer that's extremely close to 1. So you would see that that limit is equal to 1 using a numerical approach by plugging in numbers that are, trivially close to 0 but not actually 0, so that they don't break the equation. That's enough on limits for now. Next time we'll go into how they tie into slopes and rates of change and kind of start to get towards the very most basic building blocks of calculus. So hope you enjoyed this video. Give me some feedback. See you next time.